Yeah, hello everyone. Welcome again to the new session of the One World Combinatorics on Word seminar. Nice to see all of you here today. Our speaker today is Gandhar Joshi from the Open University, and he's going to speak to us about monochromatic arithmetic progressions in Sturmian sequences.
Right. Thank you so much for the invitation to talk at the One World series. Yeah, I'm going to talk about monochromatic arithmetic progressions, and I'll keep calling it maps, and I'll make sure that I don't say anything about other types of maps anywhere else. So this is joint work with Dan Rust, my supervisor. And okay, let's get started. So I'll quickly define what I mean by maps. Then I'll set our objectives, and then I'll introduce the Sturmian sequences, particularly the rotation type kind of definition of Sturmians, and then if I get time, then we can quickly discuss what I have on this slope conjecture. So if you consider a random indexed string of binary digits, then a map is a repetition of a symbol at positions separated by a constant difference d in a sequence over an alphabet. So the theorem, which was an answer to Bode's conjecture by van der Waerden, was if you let k and n be integers, then positive integers, then for every k there exists a long enough string of length n such that you must have a map of length k within that string. So this is the numerical side of the question, where you find word and numbers. And the last one for length 6 was done using a SAT solver in 2008. So the objective for us was, first, does a given sequence admit an infinite map for some d? And second question was, if not, if it's finite, then can we formulate the longest length of map for a particular d? So let's begin with some sort of motivation, or how we arrived at our example to test. Let A be an example, A be an alphabet. So the constant length substitution, as everybody probably knows in the audience, is where your substituted word has the same length for all the letters in the alphabet. These are also k-automatic because of Cobham's theorem. So Parshina in 2015, Aido and others, and Sobolevsky, these guys studied maps for Tuimo sequence and Rudin-Shapiro sequence, and some of their generalizations. And these were particularly constant length substitutive sequences. Because of Decking's result, it's a nice criterion where if your substitution that generates the sequence has a coincidence, which is just if you write it down, then you have the same symbol in the column, then you have an infinite map, and you can kind of see that once you start substituting into a longer and longer word. Then previous works only managed to find formulae for I'm going to call it A of D, because that's what Parshina started with, calling it A of D for the max of the length of map, but for specific families of D. So for the Thuymos word, we had if D is like a power of 2n plus 1, then the max map length is 2 to the n plus 2. They also mentioned that A of 2D is equal to A of D because of substitution, which meant that we do not have to consider even values of D for the rest of the analysis. And then they showed that for all d greater than 1, we must have a of d greater than or equal to 3. Now, they had a conjecture where they could not see from their data that a of d is equal to 3 anywhere, but they couldn't prove it. And it's a simple exercise in Walnut where you just ask if all d which are odd and greater than 1, is there a position I where you have a map of length 3, and you get false, or if you say it doesn't exist, then you get true. So Walewski found a fantastic search algorithm for the Rudin-Shapiro sequence, which actually worked much better than Walnut. If you just kept asking for particular d values, what the a of d is, it gets more complicated as the length increases. But that's only because of the conjecture that he mentioned in his paper. So hopefully there is a proof for that soon, so we can have like a more rigid sort of formula that works better than Walnut somehow. So there was a lot of constant length substitutive sequences studied for in terms of maps. And we thought, okay, maybe we can try something that's non-constant length. And the obvious sort of example that we had was the Fibonacci word, for which we found this on the OEIS, where Jeff had written first 232 values of A of D, and said that you find n plus 1 factors, and then you check if you have a map of that particular length. And he said, again, we know when we have seen all of them, so it obviously as you increase the value of D, it gets more complicated, more time consuming. So we began with some Walnut experiments, just finding patterns in whatever was possible. And we, for instance, A of D is equal to 2 in the Fibonacci word, if and only if the map begins, for the first occurrence, if a map begins at index 0 or 2. We've presented our findings at CERM in the thematic month in February 2024. And then we had 2 audience members. They came to us and suggested a couple of things. One was that if X is a Sturmian sequence, then it admits no constant arithmetic subsequence. This is just another name for infinite map, which we didn't know. So this result by Durand and Kohenesh, I hope I'm pronouncing this right, already answers question 1. Sturmian sequences don't have infinite maps. But their technique didn't really lead to finding longest maps directly. It was more of a general result about uniformly recurrent morphic sequences, and they said if it has irrational eigenvalue of the substitution index incident matrix, then you don't have infinite map. So the second audience member told us about the irrational rotation characterization of Sturmians, and maybe we could somehow study maps. So I didn't realize at that time how straightforward that was going to be, but within a month we had something really nice. So let's define Sturmians in this way. So you have a binary infinite sequence defined as a coding of an irrational rotation around a circle with 2 intervals, 0 to 1 minus theta and 1 minus theta to 1. And then in the literature, theta is usually called a slope. I have this video from Wikipedia. Hopefully it works. Oh yeah, nice. Okay, so that's how you get Sturmian sequence. So let's look at our example. I'm going to call it call the golden ratio tau. So the Fibonacci word is a Sturmian sequence where theta, the slope, is tau to the minus 2. And I'm going to keep the mod 1 sign as angle brackets because I'm going to use curly brackets for set notation later. So the plot of integer multiples of tau to the minus 2, they look like this. So instead of a circle, I broke it down into a 0-1 interval so that it's nice to finally put our method to practice, which we'll see later on. So you plot 0.39 something, then yeah, and then that's exactly what codes the Fibonacci word.
Can I ask you a question?
Yeah, please.
Well, the fractional part of n times tau to the minus 2 is a real number, not an irrational number, not 0 and 1. Did you mean by these angle brackets the floor, or what did you mean?
No, irrational part, yeah.
Well, here in your proposition, you say that the nth term of f, which is 0 or 1, is n plus 1 times tau of minus 2 at the bottom. So I'm missing.
Sorry. The interval it lands into will get the coding, right? So if it lands into interval I0, then I have 0 in my sequence.
Okay, so you don't mean what the proposition says. You mean the intervals in which it lands.
Oh, sorry, yeah. That's completely wrong statement. Sorry. Yeah, you're right.
Okay.
Yeah. Forget the proposition line. If it's a coding where if it lands in the interval I0, then I write 0 for the sequence. Okay, yeah, thank you. So as you can see, if I want to say a map of length 3 exists, then I have 3 points that are positioned in the interval I0, and the next point will be in I1. I'm sure there should be a red dot somewhere, but there isn't, so assume that, please. So hopefully most of you have now assumed what the method is going to be like. So the lemma, as complicated or wordy as it looks, it just says that if there exists a map like this, then we must have points, let's say, so from 4 tau to the minus 2 to 8 tau to the minus 2 inside interval I0. And there is a theorem which is popularly known as Weil's equidistribution criterion, which says for irrational theta, the sequence of integer multiples is uniformly distributed over the interval 0, 1. So Sturmian sequences do not admit infinite maps. And to see how, you just ask the contradiction. Suppose there are infinite, suppose an infinite map exists, then it must have all its points inside one interval, and that's not satisfied by the Weil's distribution criterion. You have to land into the other interval at some point. So now we have a nice visual version of Durand and Cohenish's result, and not only it tells us about that it's not infinite, it also lends us a nice way to count what the maximum map length is going to be. So we first define a step distance, which we call g of d, and it's a minimum of d times tau inverse and 1 minus d times tau inverse. So, which is exactly smallest distance that you can count from either boundary of the interval. So obviously, because I0 I've taken as a bigger interval, I'm going to find longest map length in the interval of I0. So that's without loss of generality. So based on the length of I1, we get two cases. First one is where G of D is less than or equal to the length of I1. And the second case is when G of D is greater than the length of I1, which is the smaller interval on the 0-1 interval. So the first case kind of looks like this, where you begin somewhere very close to 0, such that you don't have a G of D distance between that starting point and 0. And the other case is where you have something bigger than 1 minus that distance, which is this. So you're kind of going around and landing back here. If you're imagining a circle again, but otherwise it's just going backwards and counting the points that way. Oh, sorry. So yeah, so this is going to just count how many points land inside of I0 before landing into the other interval. So it's a simple division, and then you take a ceiling, because you're going to count the number of intervals and not number of dots. So number of dots points will always be one more. So if you take D equal to 5, then G of 5 is about 0.09, and then you just divide the total length of the interval I0, which is tau to the minus 1.618, and then you take a ceiling and you get the answer. And if you started plotting, you would also find the same. Now, for the other case, where the distance is bigger than the smaller interval, it looks a bit complicated, but it's not really. So you start somewhere where the first point is going to be such that the previous point has to land in the I1 interval. So 0, if you consider as the first point, then your second point must land as close as that 1 is inside I0 boundary. And now let's look at this example. D equal to 17, and G of 17 is about 0.507, which is greater than tau to the minus 2. The choice of I is it's quite obvious from Weil's equidistribution criterion. You can choose any point closer to the boundary, the second point, right? And then 71 happens to be the first occurrence where you get the maximum length. Now we just keep hopping around as long as we're inside of I0, and at some point we'll land in I1, somewhere close to this 1 on the right hand side after 19. So when you count, you get 20, but the way the formula works is that you take away the total length of the interval I0 and subtract it from G of D, which is the distance from this middle tau to the minus 1 to 0. So that's the approximate distance, which is G of D. And then you divide it by G of 2D, which is exactly the distance between two adjacent points inside this, I call it a cluster, And if you consider 0 going to 1 and then going to 2 again, so that's why it's g of 2d. And now you're just going to divide this small length by this small length, and you get a number of points. You take a ceiling because you're getting the number of intervals first. So add 1 using the ceiling to get the points. And then you multiply by 2 because there's 2 clusters forming because the golden ratio to the -2 is between a half and a third. So you get 20, and you can test that with a random choice of D as well. So probably gone a bit too quickly. So please ask me at this point if you have any questions about the formula. Okay. So generalizing was slightly extra bit of case analyses, but you have this really nice set of formulae where you can ask any slope theta between 0 and 0.5, and that's just you can take something bigger, but you'll just have a flip of that Sturmian word. And for any D, you can find the max length of the map. Here, K is K depends on what the length between the bigger interval and G of D is. And that sort of determines 2 cases where you get slightly different situations. So yeah, so I think I have quite a lot of time, so I can discuss this slope conjecture in detail. So we plotted, this was also way before we had this specific formula for the for A of D, and the conjecture was if you plotted A of D values against D, then A of D -1 just to cover even spots here. So A of D to D ratio is bounded above. A of D -1 over D ratio is bounded above by 1 plus tau to the -2. And it looks obvious when we look at values, and there are few approachable conditions that we can say, okay, it helps us sort of imagine that it can be true. But let's look at this example. Maybe I can just say quickly that these local maxima are exactly where the Fibonacci numbers occur. So 8 has a local maxima, 13, 21, and so on. So let's see one such example between a Fibonacci number, A of D equal to Fibonacci number, and the next one. So the 3-gap theorem tells us that the distance between j tau mod 1 points on the interval 0, 1 have exactly have at most 3 distinct pairwise gaps, and if D is between Fn minus 1 and Fn, then the smallest gap length is this, which gives us the reason why A of D value here is a local maxima. To see that, we just see that we check that G of Fn, we get tau to the minus n, and if we take this identity, Fn plus 1 minus tau Fn equal to minus 1 to the n over tau to the n, and we take mod 1 on both sides, we'll end up with this formula for A of Fn, and that's why you see these maxima in the slope. Now, what about this middle one? And you'll see that 17 is exactly Fn over 2 for Fn equal to 34. So how does that work? Before that, let me just say that we have this step slope that works. So we can say that there are no values reaching above this line. So let's see for another formula where for the first formula where G of D is less than or equal to tau to the minus 2, we have that for all D less than Fn, we must have A of D less than or equal to A of Fn minus 1. Again, from the 3-gap theorem, because you're not going to find, so the smallest G of D value, G of D distance until then is going to be Fn minus 1, which takes care of this maxima. And the next value is this. So there is no smaller value than that for G of D, which translates to a maxima for A of D. Then we have another step bound for Fn over 2 for all values where G of D is greater than tau to the minus 2. So these are not all the values in that interval between 4 and 17. But these are values where G of D happens to be greater than tau to the minus 2. And for all such D which are less than or equal to Fn over 2, A of D must be less than or equal to A of Fn over 2, which is also a similar exercise where you find that Fn over 2 also gives you a smallest G of D distance, which translates to a maxima for A of D, because G of D, if you can recall, is in the denominator for these formulas. So that's why we can say that having a minimum G of D translates to a maximum A of D. And now you've seen that the red line took care of values where G of D was less than or equal to tau to the minus 2, and the green line took care of the values where G of D was greater than tau to the minus 2. So we can surely say that this now can be considered as the new bound. And now if we can sort of zoom in a little bit and check if we have anything in between for values which are between the Fn here, for example, 13, and the next Fn over 2 that appears here, which is exactly this. So the Fn minus 2 is 13, and Fn over 2 is this 17. And you only have a difference of 1 or 2, depending whether n is odd or n is even. So it's quite easy to see that there is nothing that's going to be in between, that's going to top, go over this bound, a small triangle that you can see here between the dotted line and the blue line. And finally, we consider a D where G of D is greater than tau to the minus 2, coming to the interval between 17 and 21, where A of D crosses the slope, possibly. For example, like this. Then it must have just reforming the formula that we have. It must have that A of D is greater than or equal to D times 1 plus tau to the minus 2 plus 1. 1 plus tau to the minus 2 is the slope that we have as a bound. So we just need to show a contradiction where 2 times tau to the minus 1 minus G of D over G of 2D ceiling is less than D times 1 plus tau to the minus 2 plus 1. So if we can show that, then we'll be able to prove the slope conjecture that no value of A of D goes above this. We have some empirical data where obviously we don't see any value above this. And if you can recall Pisano period, where multiples of values, divisors of Fn, so Fn over K values for particular bound K, they become constant. So A of Fn over K remains constant for a long enough interval, but we cannot be sure where it begins. So it may begin somewhere above this slope, and then it becomes constant. So we're not sure if we have enough to prove the slope conjecture. So any help in that regard is quite appreciated. And just to summarize, Sturmians are characterized by irrational slopes. We now have formulae that count the longest map lengths for any D for Sturmians with slope theta. And this technique hopefully can be extended to other families of sequences defined using irrational rotation, but probably quite a lot difficult than this case. An example that comes to our mind is higher dimensional billiard sequences. Hopefully, I hope to revisit this problem someday. So thank you. Yeah.
Oh, thank you very much. Does anyone have any questions? You had mentioned that there was some general result for morphic sequences.
Yeah.
Was it Duran and Goihamej?
Yeah.
What exactly or approximately is that result saying?
So it says you have a substitutive sequence which has irrational eigenvalue. Then you must have no infinite map in that sequence, and I'm not sure of the details of the proof. Dan has tried to explain it to me, but I wasn't quite sure. So maybe. Oh yeah, dynamical eigenvalue. Okay, yeah.
Okay.
So not yeah.
Okay. Interesting. I'll have to check that out.
Yeah. So they also talked about other families of sequences and what happens to arithmetic subsequences in those families.
Okay. Oh, Jean-Paul.
Yeah.
Yeah, I have a vague question. There's in a paper by I think Klemanchik and Mulna, what they call aperiodicity, which is that the average, I mean the mean on each arithmetic progression is zero. So I wonder how how it could be studied in this context. I mean, so instead of having no arithmetic progression, I mean no infinite arithmetic progression, just want these all the arithmetic progressions having the sequence being of average of mean zero on all arithmetic progressions.
Is there an example that I can look at
Uh,
for that? Like
wait a minute.
a sequence that has this property.
Wait, I think in the paper by maybe I have it somewhere. Maybe in this paper there is a sort of canonical example. I'm not sure. I mean, they
I'll check this paper.
yeah, this is a paper that the title is just a minute. The title is Automatic Sequences are orthogonal to aperiodic multiplicative functions, and it is on the archive and by Müllner and Lemanjic.
Okay.
Lemanjic and Müllner, and I think it was published in the Discrete Dynamical and Continuous Systems or something like this. I can send you the precise reference as soon as I
Thank you.
find it.
Yeah, I'll look it up. Thank you.
Yeah. Thank you.
Yeah, I have a question about this Durand theorem. So I- I'm looking at it, and it talks about uniformly recurrent morphic sequences.
Yeah.
But your statement here is about Sturmian sequences, and most Sturmian sequences aren't morphic. So did I miss something?
No, the theorem as it was for morphic sequences, and not necessarily the theorem had a corollary or a proposition that took from this property of sequences having the dynamical eigenvalue as irrational. So it was as almost a what do you say, consequence that that if it's a Sturmian sequence, then it has no constant arithmetic subsequence. So it was a consequence of a more general result.
Okay.
Yeah, I'm not sure how it translates, but we just had this as a in terms of what's done before.
I get it. Okay. Yeah. So it's not about uniformly recurrent, but more general than that.
Yeah.
Yeah. Okay. Thanks.
Are there any other questions?
Can I?
Oh yeah, Gabriele.
Hey, hello, Gandhar.
Hi.
These results you presented reminded me somehow the techniques that we developed in a paper with Filippo Mignosi, Jarkko Peltomäki, and others.
Yeah, it was Jarkko who was the second audience member who told us about your paper and look at the workings there. So
That's interesting.
that helped a lot because he tried to explain it over a circle, and I could not for the life of me do anything. But then we thought about, okay, let's break it down and look at it as an interval. But yeah, after that it was quite straightforward. Just nice algebra that just yeah.
In view of this, I think that the generalization to interval exchange transformations and other similar dynamical systems can be easily doable.
Yeah. I think I met someone in Nancy who was looking at these what the name that you said.
The name that I said when?
The type of transformations that you said.
Interval exchange.
Yeah, interval exchange transformations. Yeah, I just don't get. I mean, I haven't read much, but I just don't get where you lose track of the points at some point. So
Mhm.
I'll have to read more. That's why I discussed it with that person. If the methods can be applied there.
Okay, and I think that also Melody Andrieux is working on a direction that is not the same, but has some similarities. So maybe you can profit of a collaboration with Melody Andrieux and Léo Vivion.
Okay, thank you, Melody, and I'm not sure how to spell it, but I'll hopefully
Andrieu.
And okay, yeah. Thank you.
Jean-Paul, did you have a question?
Just to say that I wrote the reference, the DOI number of the paper I mentioned on the chat.
Oh, yeah. I saw. Thank you.
Okay.
Yeah, and Dan also posted in the chat that it's maybe worth mentioning we still know very little about A of D for 2A Morse or any chaotic sequence without infinite maps.
That was also quite, an empirical study where you can only find some families like power of 2 and anything around that, and that's it. So.
All right, does anyone else have anything? If not, thank you again, Gandhar.
Thank you.
Thanks to all of you for coming today. And we'll see you in 2 weeks for our next talk. So until then, bye everyone.
Thank you guys. Bye.